In this video, we will implement stack using queues. That is, we have to implement functionalities of a stack data structure using queue data structure. So let's quickly recap how stack and queue data structures work. Queue is a FIFO, that is first in first out data structure, whereas stack is a LIFO, that is last in first out data structure. Now let's quickly list down the functionalities of a stack data structure. In stack data structure, we have a top pointer which we use to perform all the operations on a stack, which include push, that is inserting an element to the top of the stack, pop, that is removing an element from the top of the stack, top to get the element at the top of the stack, size to get the total number of elements in the stack, and finally empty to check if the stack is empty or not. So now let's quickly list down the functionalities of a queue data structure. In queue data structure, we have two pointers, the front and the rear pointer, where insertion always takes place at the rear, while the removal of an element always takes place from the front. With queue data structure, we have the following functionalities. Enqueue, that is inserting an element at the rear of the queue. Dequeue, that is removing an element from the front of the queue. Front to get the element at the front. Size to get the total number of elements in the queue. And finally empty to check if the queue is empty or not. Now to make a stack using queue, let's consider the front pointer of the queue as the top pointer of the stack. And now all we need to do is add functionalities of a stack data structure to our queue data structure. So let's list down their functionalities side by side to compare what all functions are same in both the data structure and what functions we will have to implement to create a stack using queue. So starting from the bottom of the list, we see that the empty method in both the data structures is same, that is it tells us whether the data structure is empty or not. Moving upward, we see that the size method is also same in both the data structure, which gives us the total number of elements in the data structure. Now comparing the top and the front method, as we have decided that the top pointer of the stack will be represented by the front pointer of the queue, we can say that the front and the top method both have the same functionality as they give us the element at the starting of the data structure. Similarly, comparing the pop and the dequeue method, we can say that they have similar functionality as they both remove the element from the starting of the data structure. Now finally, comparing the push method with the enqueue method, we see that the push method in the stack is to insert the element at the top of the stack, and the enqueue method in the queue is to insert the element at the rear of the queue. Therefore, they both perform different functionalities, and we are missing out on a push method in the queue through which we can insert the elements at the front of the queue. Because if we are able to do that, then we'll have all the functionalities of a stack data structure in the queue data structure, and we will be able to implement stack using queue. So by comparing the functionalities, we now know that we have to make a push method to insert an element at the front of the queue to achieve all the functionalities of a stack data structure using queue. So let's see how we will implement the push functionality in the queue data structure. For that, let's take an example. Say we have to insert the elements 1, 2, 3 and 4 to a stack S, which we will represent using queue. For that, we will take two queues, one primary queue and one secondary queue, where the primary queue will be our stack S, and we will use the secondary queue to achieve the push functionality of a stack. So if we have to insert any element, firstly we will enqueue the element in secondary queue, and while the primary queue is not empty, we will insert the element at the front of the primary queue to the secondary queue, and we will remove that element from the primary queue. Finally, we will swap the primary queue with the secondary queue. So let's understand how this push functionality works using the example. So firstly, we have to insert the element 1 into our stack S, which is represented by the primary queue. So following the steps, we will enqueue the element into secondary queue. Therefore, both front and rear pointer of the queue are pointing to the element 1. Next, while the primary queue is not empty, we have to enqueue each element from the primary queue to the secondary queue and remove that very element from the primary queue. But as we can see, initially our primary queue is empty. So we will skip this step and move to the next step, which is we will swap the primary queue with secondary queue. Now again we have to insert the element 2, so we will enqueue it to the secondary queue. Therefore both front and rear point to the element 2. Next, while the primary queue is not empty, we will enqueue each element at the front of the primary queue to the secondary queue and we will remove that element from the primary queue. Therefore, we will insert the element 1 to the secondary queue and we will remove the element 1 from the primary queue. Now as the primary queue is empty, we will swap the primary queue with the secondary queue. Now again, to insert the element 3 at the top of the stack, that is front of the primary queue, we will enqueue the element in secondary queue, and then while the primary queue is not empty, we will insert the element at front of the primary queue to the secondary queue and we will remove that element from the primary queue. So we will insert the element 2 from primary queue to the secondary queue and we will remove that element from the primary queue. Following the same steps, we will insert the element 1 from the primary queue to the secondary queue and then we will remove the element 1 from the primary queue. Now in the final step, we will again swap the primary queue with secondary queue. Now finally, to insert the element 4, we will enqueue it to the secondary queue. Then we will insert the element at the front of the primary queue into secondary queue and we will remove that element from the primary queue. Again, we will insert the element at the front of the primary queue, which is 2, into our secondary queue and we will remove the element 2 from the primary queue. Finally, we will insert the element 1 into secondary queue and we will remove that from the primary queue. And now as our primary queue is empty, we will swap the primary queue with secondary queue. So using these steps, we can see that we have achieved the push functionality of a stack. That is, we are able to insert the element at the top of the stack, which in this case is the front of the primary queue. So now if you want to visualize the following example in the view of a stack, it will look something like this, where we have inserted the elements 1, 2, 3 and 4 into our stack S and our top or front pointer points to the element 4. Now let's write some code and implement this in C++. So firstly, we will include the library IOStream. We will include the library queue to use the inbuilt queue data structure in C++. We will use the standard namespace. And now let's begin writing our class to implement stack using the queue data structure. So we will declare a class stack in which we will define our two queues, primary and secondary queue, both of type integer. Next, we will write down all the functionalities of the stack data structure, which will be public. So starting with the push function, which takes one argument, which is the element to be inserted into the stack. And following the steps that we did before, we will enqueue this element into the secondary queue. And while the primary queue is not empty, we will insert the element at the front of the primary queue into the secondary queue and we will remove that element from the primary queue. Finally, in the last step, we will swap the primary queue with secondary queue. For that, we will take a temporary queue and make it equal to the primary queue. Then we will make the primary queue equal to the secondary queue and the secondary queue equal to the temporary queue. With this logic, we have successfully implemented the push functionality. So now let's move on to the next functionality, which is pop, that is removing an element from the top of the stack, which is similar to the dequeue function in the queue. So firstly, we will check if the queue is empty, we will return from the function. Else we will simply perform the dequeue function of the queue. Next, to implement the top functionality of the stack, which returns the element at the top of the stack, we will first check if the queue is empty, we will return -1. Else we will return the element at the front of the queue. Finally, let's create a function to display our stack. For that, we'll create a temporary queue and assign the primary queue to it. And while the temporary queue is not empty, we will display the element at the front and we will dequeue that element to one by one display all the elements. And with this, we have successfully implemented a class to represent our stack data structure using the inbuilt queue data structure in C++. So now let's see this in action in our main function, where we will create an object of the class stack and we will insert the elements 1, 2, 3 and 4 to the stack S as we did in the example. Now if we call the display stack function in S, we will get the output as 4, 3, 2, 1. That is, the element at the top is 4, after that 3, 2 and 1 in our stack. Next, if we want to display the element at the top, we can use the top function, which will give the output as 4. Finally, if we want to remove or pop the element from the stack, we can use the pop method, which will remove the element 4 from the stack, and we will have the element 3 at the top of the stack. Thank you for watching this video.